All right, so I want to start this off by talking about how magnetic and electric fields are related in an example that should be pretty familiar to you because we have used quite a bit of Lenz's law so far. So let's first talk about a loop in a strengthening magnetic field. So I'm going to have a magnetic field that points into the page. And here's my loop. I'll make this a little bit bigger. And there's my loop. And we can follow some hopefully familiar steps of Lenz's law, and I'll follow them the way that we did in class, which is that I'll have an external field that points into the page. And because it's getting stronger, that means that the flux is increasing. So Lenz's law says that the induced field will oppose that change. So the induced field must point in the opposite direction to the external field. So that is that way. So let's draw that like that. And there is my B induced. It looks like that. And then we can use the right-hand rule to figure out what direction the induced current must be flowing, which is that if I want my fingers to point out in the middle of the loop, then my thumb will point in the direction of the current, and you can see that my thumb is pointing in a counterclockwise direction. So I induced is counterclockwise. All right, so just to add a little bit on here, I also want to think about what direction electrons are going. So we know that we've defined induced current as, that we've defined current as the flow of positive charges, but it's actually negative charges, electrons, that are carrying the charge in a configuration like this. And so they're actually going the opposite direction. So the motion of electrons is going to be the opposite of that, so they'll be moving clockwise. All right, so here's a question. So let's think about a single electron right here, which we know is moving to the right. There has to be some sort of force to cause that electron to move and to curve and to accelerate. Without a force, changes in motion never happen. So what force is it? Magnetic forces aren't going to cut it. What we need to think about here is the force that we started in the very beginning of this semester talking about, which is rather than talking about the magnetic force, an electric force due to an electric field could certainly cause this electron here to scoot around in that circle. And we know from the very beginning of this semester that electric forces and electric fields are parallel to each other for positive charges, but for negative charges, the electric field points in the direction that's opposite to the force. So just to sort of remind you a little bit about these things, the electric field here is the sheet analogy. So this is the thing that makes the shape of the sheet. And then when we place an electron or any other charge in that field, we know how it would move, what kind of forces it would feel. But long story short here is that in order to get this electron to move to the right at the top of this loop, we need an electric field that points in that direction to the left. And we could rationalize that this same thing is going on everywhere. So here, electrons will be going up, and in order to get that, we must have an electric field that points down. The electric field here has got to be everywhere tangent to this circle, traveling around in the circle. So this electric field is actually an induced electric field that we haven't really talked about yet. But it must be true that every time you induce a current and you induce a magnetic field, you also induce an electric field. And I want to point out a really important point that will always be true about electric and magnetic fields, whether they're the external or the induced fields, which is that in this example, we have the electric fields always being in the plane of this paper. And we also always have that the magnetic fields, even though they point in opposite directions, they are always pointing in the plane, pointing into or out of the paper. So electric and magnetic fields are always perpendicular to each other like that, and that will be a general thing that will always be true. There is also another thing that's worth pointing out, which is that there's nothing here that actually requires there to be a physical loop. Electric field is going to be induced. Remember, the field doesn't require charges. The electric field just exists, is the thing that exists to show you sort of what forces an electron would feel if it were placed in there, but it doesn't actually have to have a charge or an electron to exist. So there is actually an electric field everywhere that's induced. That would still be everywhere tangent to this circle. There's one there. I could draw a bigger one, go around in a circle up here. Always pointing in that direction. All right, so just to summarize a few points that we've already got, that we've already said, but to just write them down, some notes about this is that just as, oh, and we actually haven't said this one. So just like this external magnetic field that we started out with, which was these X's that were into the page, was able to induce an electric field, you can also go the other way around. We could have started now from an electric field and had that induce a magnetic field. So just as we'll say changes in magnetic fields induce electric fields. Electric fields can induce changes in magnetic fields. Another thing is that this occurs whether or not charges are present. And last is that these electric and magnetic fields are going to be able to sustain themselves. And what I mean by that is that they are going to be able to create a wave that propagates in all of the same ways that waves have propagated for other in previous chapters. So all right. So from there, let's do an application, which is the example that your book starts off with, which is kind of a conceptually dense example. It's talking about antennas, but I think it's a really nice and relevant one that also allows us to make some connections back to chapter 21. So I just want to redo that example, which is an application to antennas. Okay, and so your book has a little diagram, which I'm going to simplify just a smidge. And just imagine that we have an antenna. So we basically have two long conductors that are connected to some sort of AC source. So, and we'll just imagine it right at a certain instant where we have an AC oscillation, and for an instant, we're going to imagine positive charges going up here and negative charges flowing down here. So now this isn't really a full loop, so we're not going to have sort of current flowing around in a circle, but as long as we're AC current here, we can constantly be flipping whether the electrons are down here or up here and down here and up here, which means that we can actually constantly be having a current that's flipping directions. So it's going to be going in one direction, another direction, in one direction, and another direction. So what's going on here is that we have current is the flow of positive charges. So where the positive charges are, that's where the current is going to. So at this instant, we have a current that looks like that. Okay, so I'll write this as my first step, which is that I have an AC oscillation, and at one instant, at this instant, electrons are moving to the bottom, and that means that current is going up. So we know that if current is traveling in a wire like this, that is going to create a magnetic field. There will be a magnetic field associated with that. We can use the first right-hand rule to figure that out. So if I put my thumb in the direction of the current, my fingers are going to wrap in the direction of the magnetic field. And so what I see there is that the magnetic field associated with this is going to look something like that. So that is the B. So it's wrapping around so that it's going into the page on the right-hand side of the wire and out of the page on the other end of the wire. So we can have a second step, which is, by right-hand rule 1, B is into page, so the magnetic field, and this isn't an induced magnetic field, this is just a normal old magnetism magnetic field. We have a current, there will be a magnetic field associated with that, is into the page on the right and out of the page on the left. And next is that we also know that electric fields point from positive charges to negative charges. That's with the sheet, right? The positive it points downhill from positive to negative charges. And so for reasons that I'm certainly not going to get into, rather than just going in a straight line right next to the antenna, it doesn't go straight from positive to negative. It sort of curves a little bit on its way. And I just want to draw this and point out that certainly this is just a very first chapter of the semester, a chapter 16 thing, right? We know that electric fields point from positive to negative charges. There's nothing that required any sort of induction or electromagnetic waves. And once again, we see that we have found that magnetic field and electric field are perpendicular to each other. And what's actually going to go on here is that everywhere the magnetic field is going to look like that. So let's write that. So 3 is that E so that the electric field points from the positive to the negative charges, just as we have. And we have found that the E and B, the electric field and the magnetic field, are perpendicular to each other, just as we expected. So a short time later, this is not going to be the configuration anymore. Rather than having, remember this is an AC signal, so it's going to be constantly flipping. Rather than having the positive charge up here, we're going to end up with the positive charge down here. So a very short time later, this is going to instead look like this. And I'll skip some of the analysis that we did, but we'll have negative charges on top and positive charges down the bottom. And we can have that current now, rather than flowing up, will be flowing down. And that means that the magnetic field is going to flip. So rather than being into the page here, it'll be out of the page here. And like that. And we will have electric fields pointing from the positive to the negative, looking something like that. And I'll just fill in the same thing where in this area we have magnetic fields that are out of the page as well. But now this hasn't disappeared, it's just been replaced. So what's going to happen to this is it's going to behave like any wave. It's going to propagate out so that we can make space for what's coming. So this part hasn't disappeared, it's just farther out here now. So you can imagine that we still have what we had before. It just looks like that. And this whole process of oscillating electric and magnetic fields happens every time this circuit flips. So if this is a 1 million hertz signal, that means 1 million times per second, this is flipping up and down, and we're creating a wave that goes up and down 1 million times every second. So a couple of notes about this is that radio waves can be sent out via antenna like this. So this is why you have those giant radio towers on the tops of hills usually, so they can send out a really high power electromagnetic wave that'll propagate out for a really long time. You can also receive signals via a radio wave like this. So radio waves are detected by antenna. All electromagnetic waves can be detected by antenna. And the way that they're going to be detected is by the principle of resonance. So a radio antenna is going to have some sort of length of this conductor here that is resonant with the frequency of this wave. So if an electromagnetic wave approaches the antenna, it will excite a resonant frequency on that antenna and make it oscillate up and down. If you want to have your best reception, then you want the length of this antenna to be about 1/4 of a wavelength of the wave. And that maybe sounds familiar to you because we talked about an open and a closed tube having a resonant frequency that looks something like that for its lowest mode in chapter 12. And this is very much like an open and closed tube. So this antenna is behaving like a tube that's closed on one end and open on the other end. So if you want it to be resonant with an incoming frequency, then you want it to be a length that's about 1/4 of a wavelength long. So just as a little fun fact, the wavelength of AM waves is about 300 meters. So that would mean that in order to receive a wave, you would want it to be 75 meters long. So we don't do this to receive AM waves, and it's why you need a separate kind of antenna for your FM waves and your AM waves, right? You don't, like, I had a car once that did great receiving AM waves, but it was horrible at receiving FM waves, I think probably because the antenna wasn't connected. You need totally different antennas to receive these. What we do for AM antennas is actually not use an antenna like this. Instead, so this antenna will be something that detects the electric field, that's resonant with the electric field. And an antenna, we usually use a solenoid or a coil that can be resonant with the magnetic wave as it comes through. So that is what we do for AM antennas. All right, so I want to do another example, which we'll call example 22.1. And this example is done out on the lecture slides as well, but to avoid switching back and forth, I'm just going to do everything on the paper. Is that I want to design a coil for an AM wave, and I want to figure out how I should orient that coil to make the AM wave work, to make my my radio detect the wave. So I have AM waves moving to the right. How should you orient the coil antenna? And let's just say that here's my source, so it's going to send out some things. And here's what my electromagnetic wave is going to look like. It'll have electric field and magnetic field, so I will draw the electric fields as being like that. So this green will go for electric fields. We're oscillating up and down in the electric field. And we'll also have some magnetic fields that are going to be coming into and out of the page. I certainly don't expect you to memorize anything about whether or not exactly how they're perpendicular to each other. So I'll just sort of tell you that this is going to be out of the page here and into the page here. And I'll try to draw my X's so they have some sort of magnitude information where the field strength is strongest in the middle here, where the amplitude or the kind of departure from the equilibrium is the biggest. So big air in the middle, small. And that'll be my magnetic field. And where do you want to take a loop and put it here? So how should it be oriented? I'll give you a minute to think about that. So I'll use a very, very high-tech loop here. So basically, we know that an induced field will be created inside this loop in the presence of a changing magnetic flux. And we have a wave, which I said was going to the right, but I didn't actually write it. So at this speed of 3 × 10⁸ meters per second, this wave is scooting to the right. And how do you want to orient your wave so that you can sort of catch these changing magnetic fields? And I think the way that I have this oriented is probably the right way. A way that would not work would be if I oriented my coil like this. So then as the wave passes through, it would be sensing the up and down motion of the electric field, but the in and out motion of the magnetic field changing back and forth like that actually would do nothing here. So we would want to orient our coil like this. So I will draw that. And this is actually a real thing, and I'll show you in class with a radio, an AM radio, that there is a way that you can orient your AM tuner so that you get good reception. And then if you turn that 90 degrees, so you turn your radio 90 degrees, you won't get very good reception anymore. So these are, unlike FM tuners, these are really sort of directional dependent. All right, and so this, I'm going to write some things down. So where the change in flux, where the change in magnetic flux, I'll put a little subscript B, is maximum. You'd place the loop. So put the loop in the plane of the page. So one other thing that I wanted to point out while we're here is that this principle is also actually exactly how your microwave oven works. So water molecules have a really strong dipole. So they have a really strong negative side and positive side. And if they're placed in the vicinity of an electric field, then they're going to flip back and forth. So just to sort of diagram this out a little bit. So water molecules with their strong dipoles are going to rotate because of the changing electric field inside the microwave oven. So if I imagine some time here where the electric field that is flipping on the time scale of gigahertz, because that is the time scale of microwaves. So microwave ovens actually do use microwave radiation. If you imagine being a little water molecule in here where your hydrogen molecules are attached to an oxygen and you have a strong negative end here and positive end here, so you sort of have a dipole that points to the right. In the presence of this electric field, this thing is going to rotate. So it's going to start out in this direction and it's just going to twist a little bit. Water molecule. And then an instant later, the electric field is going to flip directions. So some later time, there's what my electric field looks like. And that same water molecule is now going to want to flip in the opposite direction. So it's going to start rotating in that direction. And what goes on here is that you sort of continually have this water molecule, and actually there's nothing that requires this to rotate in the opposite direction. It can keep rotating in the same direction. The main point is that as this water molecule, as the electric field strength keeps changing directions, this water molecule is going to be constantly changing back and forth in much the same way that a motor worked. And so this water molecule is going to be spinning faster and faster. So what we're doing is we're taking the energy from the electromagnetic waves, so that energy from the microwaves, and we're turning that into rotational kinetic energy. And from there, that can warms up the food. So once you have those water molecules vibrating, then the molecules next to the water molecules will vibrate over and over again. Which brings me to one of my favorite tricks, which is things that you put in the microwave that don't have water in them, they don't heat up. So if you've ever put maybe a plate in the microwave with nothing wet in it, you can stick that plate in there for a minute and you pull it out, and as long as the air wasn't very wet to start off with, you'll be able to touch that plate. This is why when you heat up tortillas, it's a good idea to put a little sheet of water on top of that. It helps things warm up more evenly. So the microwave, the frequency of the microwave is sort of specially tuned to be, resonant isn't exactly the right word here, but I'll use it anyway, be sort of resonant with the oscillation of these water molecules. So the presence of water is actually what makes your microwave oven work. All right. And last but not least, I just want to throw some equations down. So we have first is that the speed of waves is something that we call c. So that is 3.0 times 10 to the 8 meters per second. And that is the speed of light in a vacuum. This is as fast as it can travel. When light is going through anything that's not a vacuum, it'll actually be a little bit smaller than that, or a lot smaller than that, depending on things. It's very close to this number traveling through air, so we'll probably still use this number talking about air. But it will matter when you start talking about light traveling through, say, glass or some other medium. And that's going to be the basis of things like refraction. And it turns out that two constants that we have used all semester determine that speed. So epsilon naught and mu naught were two constants that are on your equation sheet. If you kind of multiply them, these things together, you'll get the speed of light. It also turns out that you can figure out the speed of light as being the ratio of the magnitude of the electric field to the magnitude of the magnetic field. And we shouldn't forget that the speed of light is frequency times wavelength. So that'll allow you to sort of figure out wavelength and frequency of waves. Because remember, this number will always be a constant number here. So these things will vary in a way to make one going up means the other one has to go down. Just like this is a wave, so like any wave, it has an intensity. So we defined in chapter 11 that the intensity of a wave is its power, so the power from the source divided by the area that it spreads out over. And that's still going to be here. So we'll have power of the source divided by the area of a sphere, which is 4 pi r squared. And it turns out that when you plug in numbers and do some derivations, you can define that the intensity of an electromagnetic wave depends on some constants, but most importantly, it depends on the square of the electric field strength. If you do a little bit of other rearranging, most notably by kind of plugging in things from this equation, you can also show that that is equal to some other constants times the magnetic field strength squared. So it depends on the square of the magnetic field strength. And you could also write this as having both an E and a B in it. E times B over 2 mu naught. Any of those will work and get you there. And I think the important thing here is that both of these have constants, but they depend on the square of either the magnetic or the electric field together. All right, so let's do one quick example before we return to the PowerPoint slides and finish off a few things, which we'll call example 22.2. Again, this one is worked in the lecture slides, which is a digital cell phone. Some typical numbers about your cell phone is that its operating frequency is 1.9 gigahertz. That's a microwave. And the power is about 0.660 watts. So it's consuming 0.6 joules every second that it's working. And what are the amplitudes of the magnetic and electric field 10 centimeters away? So we have that intensity is going to be power over area. So we'll just plug in that formula so that the intensity of that wave is 0.6 watts divided by 4 pi r squared. So r will be 0.1 meters. And putting those numbers into my calculator, I get 4.8 watts per meter squared. And now I can solve for what E and B are just by using whichever one of these equations I'm interested in. So if I solve this equation here for E, then I'll pull everything over to one side and take the square root of everything, and you will get that that is 2 times I divided by C times epsilon naught. The square root of that. So that is 2 times 4.8 watts per meter squared divided by 3 10 to the 8th meters per second divided by epsilon naught, which is 8.85 10 to the negative 12th coulomb squared per Newton meter squared. And that is 60 volts per meter. So just being in the atmosphere, a typical atmospheric electric field, being in the world is about 100. So this is a number that's smaller than just you're experiencing living at every moment of the day. For the magnetic field, I'm not going to resolve that whole thing. I'm just going to use this equation because that'll be easier. But this equation here would get you the right answer as well. But this one's going to be a little simpler. So I will use that B is the electric field divided by the speed of light. And that ends up being 2 times 10 to the negative 7th Tesla. You may, just to compare this, the Earth's magnetic field is 10 to the negative 5th. So, and actually if you do out the full numbers, it ends up that the Earth's magnetic field is 250 times stronger than that magnetic field there. So I like to do this example as a concrete sort of example as to whether or not your cell phones are going to give you cancer. The radiation that is coming out of your cell phone is weaker than the Earth's magnetic field and weaker than sort of living on Earth at every moment. And this will be even more relevant when we start talking a little bit about photons, which we'll talk about when we do this in class, which is that, you know, this microwave radiation that's coming out of your cell phone is low energy radiation that isn't capable of kind of ionizing you or doing the things to you that cause radiation poisoning. So, yeah, your cell phone is may be dangerous for some reason, but it's not dangerous because it's emitting radiation. And that is the end of that. So I still